I would now like to go over some of these notes at the end of chapter 10, and it's the end of the notes that I've posted. And these are great questions to think about and questions about the application of exercise physiology. And I think I'm going to go through most of these different questions. Maybe not actually in order, but we'll go through them. So, what is the ventilatory threshold? And I think I have a graph on the next slide of what this looks like, and it's similar to the lactate threshold. And this will help us answer a couple of different questions. So if we would look at breathing rate, so here's breathing rate or ventilation. Actually, that's not true, not breathing rate, but this is ventilation. So how much air are we taking in and out per minute? And this is exercise intensity, or VO2. And so on this graph is this red line, I guess, that describes ventilation. And at some point, so right here, I guess at 2.5 liters of oxygen per minute, this ventilation sort of exponentially goes up. So it changes the shape of the curve. And notice that that is actually at the exact same, pretty much the exact same point as this lactate threshold. And we talked earlier about some causes of this lactate threshold, where now we're seeing more lactate in the blood. And so if we're seeing more lactate, or once it's originally made, it's called lactic acid, remember? So one way to buffer or get rid of lactic acids is by this bicarbonate ion. So bicarbonate ion is HCO3 minus. It will combine with acids, and here it's the H plus portion, the hydrogen ion of that acid, to make this H2CO3 that's circulated in the blood. And then over on the left-hand side, this is what we blow out. So we're blowing out some water vapor, and obviously we're blowing out CO2. And this CO2 came from the buffering of these lactic acids, or different metabolic acids like lactic acid. So when we're increasing the rate of lactic acid formation, we're also increasing our breathing rate to blow off that additional CO2s that came from lactic acid buffering. And this actually relates to what's called the talk test, and maybe some of you have heard of this. So a very simple way to describe exercise intensity. If you're exercising so hard that it's difficult to carry on a conversation, now this is above this lactate threshold, and above the ventilatory threshold. I'm breathing, when I'm exercising, I'm breathing hard. It's difficult to carry on a conversation. If you want today's exercise to be relatively easy, it's going to be below the ventilatory threshold, where it's easier to carry on a conversation. So that's called the talk test. Can R values be greater than 1? And the short answer is yes. And if you remember, what are R values, or R or RER or RQ? I sort of use all the terms or all the abbreviations the same. And it's not exactly correct, but it's a ratio of the carbon dioxide that we produce divided by the oxygen that we're consuming. And it's a volume, so VCO2 divided by VO2. And if you divide those out, it's a ratio. And you remember this from our crossover graph earlier, that if the R value is 0.7, this is 100% fat utilization as a fuel. And if the R value is 1.0, that's 100% carbohydrate utilization as a fuel. And if we're at high exercise intensities, we're closer to an R value of 1. But can the R value be greater than 1? And the answer is yes. And the answer is yes, because when we get close to VO2 max, we are actually blowing off more CO2s. So if we look at this same bicarbonate equation, now we're buffering more lactic acids, we're blowing off CO2s, yet we're not burning any additional substrate. Meaning we're not consuming any more O2s. So if the CO2, the top ratio, or the top number of that ratio, gets bigger relative to the bottom number, remember it's CO2 divided by O2, or VCO2 over VO2, then that R value will be greater than 1. So the R value can be greater than 1. It'll be greater than 1 closer to VO2 max, and we're still burning 100% carbohydrate, but now we're blowing off more CO2s that come from the buffering of lactic acids or other metabolic acids. And maybe one additional question in here, and this is in our textbook, is called the Valsalva maneuver, which happens when we actually don't breathe during exercise. So it's a forced blowing out, a forced exhalation against a closed glottis. I'll try to demonstrate, see if you can hear this. That was my demonstration. And actually, some people, when they lift a high amount of weight, will do this Valsalva maneuver. And what can happen is that there can be this great increase in thoracic pressure. So the thoracic cavity pressure can go way up. Due to this high pressure, the blood flow coming back to the heart is going to go way down because the vena cava actually becomes compressed, it squishes. If the venous return goes down, then there's going to be less blood flow leaving the heart, and that's going to be a fall or a decrease in arterial blood pressure, and that can then decrease the brain supply to getting blood flow, and people can become dizzy and even faint. So we would recommend actually that you don't do that Valsalva maneuver if you're lifting a high amount of weight, that you continue to breathe when you're lifting. Here's a nice picture out of our textbook. One other thing to talk about is blood doping, which is at the end of these notes. And as we mentioned in some earlier notes and earlier short video, that the constant of how much oxygen a hemoglobin can carry, that is a constant, that's not going to change. But what will change is how much hemoglobin is circulating in the blood. And blood doping, so adding in more red blood cells, will do this. Altitude training will do it as well. And it can improve endurance performance by improving the blood's oxygen carrying capacity. Yet actually, if it's too much increase in blood doping, so if too much red blood cells go back in, actually the blood flow can slow down. So here in these notes, there's an increase in arterial oxygen carrying capacity. So the content of oxygen in arterial blood is going to go up because of more hemoglobin. And this will increase oxygen transport and increase in VO2 max. I mean, it can improve aerobic kind of performance. So this is a picture from the end of our book, but it'll help us describe what's going on. So here are erythrocytes, or red blood cells, and the percent of these erythrocytes relative to this whole test tube is called the hematocrit. So here the hematocrit is 45%. So these red blood cells relative to the whole blood is 45%. And if we would stick red blood cells back in, there's an increase, so an increase in the percent of control value. It can go up, 8 or 10%, and gradually over time it goes down, but this is in weeks. So if you're doing some competition, you try to time it, so you reinfuse this blood in just a couple weeks. But it can increase blood viscosity. The blood can become too thick. And erythropoietin, or EPO, is similar. It's a natural hormone that we are secreting, but you can administer external EPO, and that will increase the red blood cell volume. And it's the same idea as blood doping. And so currently, probably most males have a hematocrit of about 45%, women maybe slightly less than that. If your hematocrit is tested and it's above 50%, that's considered illegal, and so you would get kicked out of the Olympics. When the hematocrit is closer to like 60%, now it really is becoming dangerous, where the blood is so thick that oxygen transport is actually going to slow down and cardiac output is going to slow down, and that can be dangerous. So a couple nice application questions at the end of these notes.